Download this code from codegive.com, link in the description below. OK, let's dive into decision trees with a focus on the concepts and a practical code example, presented in a style that would feel like a lecture from Professor Saji K. Mathew. Welcome, class. Today's topic, decision trees, a comprehensive guide. Good morning/afternoon, everyone. Today, we'll be discussing decision trees. They are a fundamental and surprisingly powerful tool in machine learning. We'll cover the theory, the mechanics, and then put it all into practice with a Python example. Pay close attention. Understanding decision trees is crucial for grasping more advanced concepts like random forests and gradient boosting later on. What is a decision tree? Imagine a flowchart. That's essentially what a decision tree is. It's a hierarchical, tree-like structure used for making decisions based on features of your data. Each internal node represents a test on an attribute, a feature, each branch represents the outcome of that test, and each leaf node represents a class label, the prediction. Root node the starting point of the tree. Internal nodes represent tests on attributes. Branches represent the outcome of a test. Leaf nodes represent the final decision/prediction, class label or a regression value. Why use decision trees? 1. Interpretability. Decision trees are highly interpretable. You can literally trace the path down the tree to understand why a particular prediction was made. This is a major advantage over black box models like neural networks. 2. Handles both categorical and numerical data. Decision trees can handle both categorical, example color, shape, and numerical, example age, income, features. 3. Minimal data preparation. They often require less data pre-processing than some other algorithms. Normalization and scaling are often not needed. 4. Non-parametric. Decision trees are non-parametric, meaning they don't make assumptions about the underlying data distribution. 5. Can be used for both regression and classification. Can be used for predicting both continuous, regression, and discrete values, classification. The core algorithm, building the tree, recursively. The heart of the decision tree algorithm is the recursive process of splitting the data into subsets based on the most informative features. Here's the general idea. 1. Start at the root node. Begin with the entire dataset at the root. 2. Find the best split. Select the best attribute, feature, to split the data on. Best is defined by some criterion, which we'll discuss in detail shortly. 3. Split the data. Divide the dataset into subsets based on the values of the chosen attribute. Create child nodes for each subset. 4. Recursively repeat. Repeat steps 2 and 3 for each child node until a stopping condition is met. Stopping conditions. We need to stop the recursive splitting process to avoid overfitting. Common stopping conditions include: all samples belong to the same class. If all the samples at a node belong to the same class, we stop splitting. This node becomes a leaf node with that class label. No remaining attributes. If there are no more attributes to split on, we stop. The node becomes a leaf node, and the class label is usually determined by the majority class of the samples at that node. Maximum tree depth reached. Limit the maximum depth of the tree. This prevents the tree from becoming too complex and overfitting the data. Minimum samples per leaf. Specify a minimum number of samples that must be present at a leaf node. This also prevents overfitting. Improvement threshold. Stop splitting if the improvement in the splitting criterion, information gain, Gini impurity reduction, etc., falls below a certain threshold. Choosing the best split, impurity measures. The critical part of the algorithm is finding the best attribute to split on at each node. To do this, we use impurity measures. These measures quantify the degree of homogeneity, or heterogeneity, of the class labels within a subset of data. Asterisk for classification asterisk. Asterisk Gini impurity asterisk measures the probability of misclassifying a randomly chosen element in the set if it were randomly labeled according to the distribution of labels in the subset. A lower Gini impurity indicates a more homogeneous subset. Where S is the set of samples, and P_I is the proportion of samples belonging to class I. Asterisk entropy asterisk measures the randomness or disorder in a set. A lower entropy indicates a more homogeneous subset. Where S is the set of samples, and P_I is the proportion of samples belonging to class I. Note, log2 is the base 2 logarithm. Asterisk information gain asterisk this is the reduction in entropy after splitting the data on an attribute. We want to choose the attribute that maximizes information gain. Where S is the set of samples, A is the attribute, S_V is the subset of samples where attribute A has value V, and S denotes the number of samples in set S. Asterisk for regression asterisk. Asterisk mean squared error, MSE a common impurity measure for regression. It measures the average squared difference between the predicted values and the actual values. The goal is to find a split that minimizes the MSE of the resulting subsets. Where S is the set of samples, Y_I is the actual value of the target variable for sample I, and Y_mean is the mean of the target variable for the samples in S. Asterisk mean absolute error, may another option for regression, calculates the absolute differences between the actual and predicted values. Where S is the set of samples, Y_I is the actual value of the target variable for sample I, and Y_mean is the mean of the target variable for the samples in S. How the splitting actually works. The tree building algorithm finds a best split as follows. 1 for each of the features in the data set. 1 for each value of the feature. 1 split the data set into 2 sets, depending on whether the value for that feature is less/greater than a threshold or equal to that value. 2 calculate the impurity of the 2 splits combined together. 2 find the best split, the one with the lowest impurity or highest information gain, using that feature. 2 compare the best split of all the features, and chose the one with the best score, the one with the lowest impurity or highest information gain. 3 That will be the split made. Overfitting and pruning. Decision trees are prone to overfitting, especially if allowed to grow very deep. Overfitting means that the tree learns the training data too well, including the noise and outliers. This results in poor performance on unseen data, generalization error. Asterisk pruning is a technique used to reduce the size of the tree and improve its generalization performance. There are 2 main types of pruning. Asterisk pre-pruning stopping the tree growth early by setting stopping criteria, maximum depth, minimum samples per leaf, etc. Asterisk post-pruning growing the tree fully and then removing subtrees that do not improve performance on a validation set. Code example, Python with scikit-learn. Let's illustrate decision trees with a Python example using scikit-learn. We'll use the classic iris dataset. Explanation of the code asterisk. 1. Import libraries asterisk we import necessary libraries, pandas for data handling, train_test_split for splitting the data, decision tree classifier for the decision tree model, accuracy_score for evaluating the model, and matplotlib.pyplot for visualization. 2. Load data asterisk loading iris dataset using scikit-learn's built-in data sets. The dataset is stored in the X, Y, feature underscore names, and class underscore names variables. 3. Data exploration, optional, create pandas data frame to visualize the data. 4. Split data asterisk, we split the data into training and testing sets using train underscore test underscore split. The test underscore size parameter determines the proportion of data to use for testing, here, 30%. The random underscore state ensures consistent splitting across multiple runs, which is important for reproducibility. 5. Create the decision tree asterisk, we create a decision tree classifier object. Here's where you can control the behavior of the tree. Asterisk max underscore depth, this is a critical hyperparameter. It limits the maximum depth of the tree, preventing overfitting. Experiment with different values. Asterisk min underscore samples underscore leaf, specifies the minimum number of samples required to be at a leaf node. Larger values also prevent overfitting. Asterisk criterion, you can specify the impurity measure to use, Gini for Gini impurity or entropy for information gain. The default is Gini. Asterisk random underscore state, ensures consistent splitting for the tree. 6. Train the tree asterisk, we train the decision tree model using tree.fit, x underscore train, y underscore train. The model learns the relationships between the features and the target variable from the training data. 7. Make predictions asterisk, we use the trained model to make predictions on the test set using tree.predict, x underscore test. 8. Evaluate the model asterisk, we evaluate the model's performance using accuracy underscore score, which calculates the accuracy, the proportion of correctly classified samples. 9. Visualize the tree asterisk, this is a key step. We use plot underscore tree to visualize the trained decision tree. This allows you to understand how the tree is making decisions. The feature underscore names and class underscore names parameters provide labels for the nodes and leaves. 10. Feature importance asterisk, the code also prints the feature importances, which indicate the relative importance of each feature in the decision-making process. Features with higher importance values contributed more to the tree's decisions. Important considerations and best practices. Asterisk hyperparameter tuning asterisk, experiment with different hyperparameters, example max underscore depth, min underscore samples underscore leaf, criterion, to find the optimal settings for your data set. Techniques like cross-validation can help you with this. Asterisk data pre-processing asterisk, while decision trees are relatively robust to data scaling, it's still important to handle missing values and categorical features appropriately. Scikit-learn's one-hot encoder can be used to encode categorical features. Asterisk interpretability versus accuracy asterisk, there's often a trade-off between interpretability and accuracy. Simpler trees are easier to understand but may not be as accurate as more complex trees. Asterisk ensemble methods asterisk, decision trees are often used as building blocks in ensemble methods like random forests and gradient boosting. These methods combine multiple decision trees to improve accuracy and robustness. Conclusion: decision trees are a valuable tool in machine learning. They are interpretable, versatile, and can be used for both classification and regression tasks. By understanding the underlying theory and experimenting with hyperparameters, you can effectively use decision trees to solve a wide range of problems. Don't forget the importance of visualization to understand the learned model. Now, are there any questions? Professor Saji K. Mathew looks around the room expectantly.